And section 7.2 is titled Zero-Dimensional Ideals and SOS Tools. And at the time when that manuscript was written, SOS Tools was the state of the art for solving sums of squares problems. So this is the software developed by Pablo Parillo. In the meantime, there are other things you can do. So we're going to now discuss zero-dimensional varieties over the real numbers and how we can use semi-definite programming to study them. So this ties us in with the discussion of Gröbner bases in the second week of this course. So suppose you're given an ideal I in a polynomial ring S with real coefficients x1, x2, up to xn are the variables, given an ideal. And let's also assume that we're given a Gröbner basis with an explicit Gröbner basis with respect to some term. Okay, so I have an ideal, I have a Gröbner basis. We talked about the set of standard monomials, so the set B of standard monomials. So those are the monomials not divisible by any leading term. So these are the monomials not in the initial ideal. Those are the monomials under the staircase. Okay? So the set of standard monomials is a vector space basis for the residue ring. For the R vector space S mod I, I'm going to call that V. Okay? So that's the vector space V. Same V as we had 53 minutes ago. Okay? So V is the vector space. And also, for the purpose of today's lecture, let me assume that that's finite dimensional. Okay? So suppose M is finite. This cardinality is finite. So I'm actually given a zero-dimensional ideal. So I have a finite list of standard monomials, M of them. So V is an M-dimensional real vector space with a distinguished basis, namely B. Some of what I'm about to say works in general, for higher dimensional varieties, but it's much more complicated and many, many open problems. So not quite as simple, much more difficult. Okay, so this is setting. I'm going to write X for the column vector, and now I realize that that's actually bad notation, but that's what I have in the notes. So let me stick with it. So it's the column vector of length M, whose entries are B. Okay, so B is a list of monomials, right? So standard monomials, 1, x, y, x, y. And I just make a column vector that I write down all those monomials. So if something is not clear, interrupt me. This I really want to be absolutely clear. Okay, well, we have quadratic forms on V. And they're represented by matrices. A. Right, so A, if you have a quadratic form on V, then you're represented by a symmetric matrix. For example, the trace form that counts the number of real roots in a box. Okay, so we talked about the trace form. That's an example of a quadratic form on V that's we found to be useful. In one variable, that's the Hermite matrix that some of you saw after Xiaoshan's log talk on Monday. So quadratic forms are represented by a symmetric matrix. So then, if we're given such a quadratic symmetric matrix, then X transpose AX is a polynomial. In the polynomial ring. Right? So X transpose row vector times constant matrix times column vector, that's a scalar, but that's a polynomial. Right? So this polynomial has support 2 times b. So 2 times b, by which I mean, b plus b, the Minkowski sum. Okay, so as vectors, right? So in n to the n. Right? Because it's quadratic in the entries of X, they're the elements of b, and just multiply, so you get a monomial in X times some other monomial in X. Those are the monomials in 2 times b. So twice the Newton polytope. Then we have the following theorem. If we're given all these things, then the following 3 conditions are equivalent. So A, the ideal I, has no real zeros. Okay, so somebody gives you a system of polynomial equations, M, the number of standard monomials, M, the number of complex roots counting multiplicity, is finite. And now we're interested in under what condition are there no real roots at all? There are no real roots. Okay, that's A. B, minus 1, a scalar minus 1, is a sum of squares. Is SOS in V. Right? So, well, S mod I is a ring, V is a ring, right? You can multiply and so on, and you could be a sum of squares in this ring. Right? So a square is an element times itself, and a sum of squares is a sum of squares. Right? So condition B is minus 1 is a sum of squares in that ring. C, there exists a positive semidefinite matrix A such that X transpose A X plus 1 is in I. Okay, those 3 conditions are equivalent. Okay, so let's try to understand this, what this means. Okay, so suppose B holds. Let's think about this for a moment. Suppose B holds. So minus 1 is a sum of squares in this ring. So that means mod I. Right? So that means minus 1 is a sum of squares of polynomials. So a square plus a square plus a square plus a square plus something in I. Okay? Suppose there were a real root. Suppose there's a real solution. Right? Plug it into this identity. Right? So then you get, minus 1 equals a square of a real number plus a square of a real number, plus 0, right? Because whatever is in the ideal vanishes at this root. So we conclude that minus 1 is a sum of squares among real numbers, but that can't be the case, right? So B implies A. Okay? Now A also implies B, so you can reduce to the 0-dimensional case. So it turns out to the n equals 1 case. So for n equals 1, right? Well, if you have a polynomial in one variable, if it has, no real roots at all, then you can multiply. Then, you can subtract a little bit, like epsilon, and be a sum of squares. Right? So if your f, for example, is a okay. We'll do this again. So f has no real roots. Okay? So either f is strictly positive or strictly negative. Okay? Think about high school calculus, middle school, China, whatever. Whenever you studied calculus, elementary school, So either it's strictly positive, the curve is above the x-axis, or below the x-axis. So if it's below the x-axis, you place f by minus f. Okay? So it has some minimal value that's positive. Okay? Let's assume that that minimal value is at least 1. Otherwise, you multiply f by a constant. Okay? So now f minus 1 is a non-negative polynomial in one variable, so it's a sum of squares by whatever, factoring into quadratic factors over the reals or something like that. Okay? So in one variable, a implies b, but we can use a lexicographic Grobner base and the shape lemma and reduce everything. By the shape lemma, it works in n variables. Okay? So a is equivalent to b. Now what about c? Well, c is just a translation of b by the Koleski factorization. Right? So let's look at c. Right? So I'm saying that, x transpose, let's look at this. X transpose ax plus 1 is in the ideal. Right? But if a is positive definite, it has a Koleski factorization. So a is b transpose b. Right? So then we have, bx transpose times bx, that's a sum of squares, plus 1 is in the ideal. But unravel that says minus 1 is a sum of squares mod I. Right? And so that's a theorem. It's actually not a difficult theorem. And this theorem is false if we don't assume, this condition. So as stated, it's false, but other things are true. Okay? But we're just going to use this one. Let's do, just to make sure we understand, let's do an example in one variable. Okay? Let's look at the ideal I that's generated by x to the 4th minus 6x cubed plus 13x squared minus 12x plus 5. Okay, so I want to know, are there any real roots? Does this ideal, that this polynomial have any real roots? Okay, so, well, it's already a Grobner basis, right? So this is the initial ideal. So the standard monomials are 1, x, x squared, and x cubed. Okay, so I want to decide this. Is this a sum of squares? Does it have any real roots? So now we will do exactly what you will do in exercise 3. In exercise 3, we say a calculus student wants to do something, so this is what we're going to do. We're going to write this as follows. So let's look at 1 x squared x cubed times a matrix times 1 x squared cubed. So we're going to apply this thing. Okay? So x is the vector that has the standard monomial. So this is the vector x, capital X. That's x transpose. And since we don't know yet about this matrix, let's just put unknowns in there. A, B, C, B, E, F, G, C, D, F, H, I, G, H, J. Okay, there are 10 unknown entries. Okay, so let's just look at this expression. So that's this one, right? So A is we don't know, right? That's an unknown matrix. So X transpose AX, that's this expression. Okay. Okay, so you work it out, right? So this is J x to the 6th plus 2I x to the 5th plus 2G plus H x to the 4th plus 2D plus 2F. I know this is boring, but this will help you this afternoon. Plus 2C plus E x squared plus 2BX plus A. Okay, so that's some polynomial of degree 6, and the coefficients we don't know yet what they are. So that's this polynomial. So now we are given a Grobner basis. Right? So this singleton is a Grobner basis. So let's take the normal form against the Grobner basis. So I want to regard this as an element in V. V is a four-dimensional real vector space with a distinguished basis. Every vector space I ever met in my life came with a distinguished basis. Here the basis is 1, x, x squared, x cubed. Okay? So let's expand it into spaces by doing the division algorithm. So we get 2d plus 2f plus 12g plus 6h, 46i, plus 72j, x cubed. Okay? And 3 more. Okay? 2c plus e minus 26g minus 13h, 132i, 232j, x squared, plus 2b, 24g, plus 12h, plus 134i. Everything is rational arithmetic, guys. j, x, minus a, plus a minus 10g, minus 5h. That's the constant, 115j. Okay? So that's that. So now what are we supposed to do, right? C is a semi-definite program. C is an STP. This is an STP. Right? This theorem says the question whether or not I has a real root is an STP. I've written it to you as an STP. This is a semi-definite program. Right? This is a linear condition on the matrix A. There's a linear system of equations in A. The question, that's a decision problem. Does there exist a positive semi-definite matrix A that satisfies a linear system of equations? So let's derive that linear system of equations. So we need to solve, and maybe we want the 1, you know, so solve the first one, you know, is 0 for this first thing, you know, so the first 3 are all 0, and the last thing, you know, is supposed to be minus 1, right? So the equations are this linear form in A's and so on. This expression is 0, this is 0, this is 0, and this one we want to be minus 1, right? Subject to this matrix being positive definite. Okay, that's an STP, right? So we have a 4x4 symmetric matrix whose entries satisfy 4 linear constraints, and we want to find a positive definite solution. So we take that instant, so we can do this by hand, right? If you're Stephen Karp, you do this by hand, but most of us will go to MATLAB or CVX or, you know, Sedumi or something and type this in and say find A, and then in no time at all, you know, the answer comes back. And Fang can show you how to do it. Okay? So that's that, right? So in this case, it turns out there is a solution. Okay, so solution exists. So here the answer is yes, there exists a matrix. So A, yes, the ideal has no real roots. The real variety of I is the empty set. And this solution in this example, of course this is a cooked up example, you know. So if you take the solution, then you have a polynomial, right? You plug it back in. So then you have a solution to this. That's a sum of squares. And you get x minus 1 squared, x minus 2 squared plus 1. Okay, so you can actually recover, this is the same polynomial, right? So it's a certificate that there are no real roots, and you can actually recover the certificate using this numerical calculation. Okay, so this was the decision problem. Now let's move on to the optimization problem. How can we use the optimization problem? Spencer.
I just have a quick question. So in the case where, if we're in some situation where not all non-negative polynomials are sums of squares, what's the general statement for B? Is it just that negative 1 is a non-negative?
Well, then we have to increase the degree. We have to sort of go to higher and higher degree. So we'll hear a lot about this next week. But I want you to understand this case first. Really want you to understand this case. Okay, so what about the optimization problem? Well, let me call this, real root. So we could, for example, look at some real root optimization problem. So we might ask the following question. Given a polynomial, minimize f of u subject to u being in the real variety. Okay? Now, of course, Spencer, you're right. We want to do this for any real variety, right? We want to find the best point, right? The best point in the variety that minimizes some polynomial function. Right? We want to, Abraham, find the closest point or something, right? So this is, if I is any ideal, this is the general polynomial optimization problem. But today, I'm assuming that I has finitely many complex roots. And then among the real roots, we want to find the best one. Well, then we have a reformulation to see that this is an STP. So let me give you a reformulation. So find the largest lambda such that f of x minus lambda is non-negative on the real variety. Right? That's equivalent, right? So we want to find the best lower bound. We want to minimize some function, or equivalently, we want to find the largest lambda such that f minus lambda as a function on this finite set is non-negative. Is that clear? That's equivalent. Find the best lower bound. Right? To minimize a function over a set, right? So that's equivalent to saying find the best lambda, the largest lambda, such that f minus lambda is non-negative on the set.
What is S here?
S is the polynomial ring. Okay. So the only difficult thing here is R. Okay, that's because nobody has ever seen a real number, actually. But if you believe that these things exist, then you understand S. Okay. Okay, that's an STP, right? So let's reformulate this one more time. So sum of squares in an Artinian ring. So given f, polynomial in n variables, maximize lambda, that's a real number, subject to the following condition: x transpose a x minus f of x plus lambda is an I, and A is positive definite. Okay? So these two things are equivalent by the previous theorem that I erased. Right? So let's look at this. So x transpose AX. That's our way of saying B is sum of squares, right? Let's do this one more time. So if this A is positive, semi-definite, then A has a Cholesky factorization, B transpose B. then this is a sum of squares. So a sum of squares minus f plus lambda is an I. Okay, that's equivalent to saying that f minus lambda is a sum of squares mod I. Is a sum of squares in the residue ring. But that is an STP. Why is that an STP? Because we can take a matrix A with unknown entries. Little a, little b, little c, little d up to little j. Then we multiply this out. That's a polynomial in x1, x2, xn, whose coefficients depend linearly on a, b, c, d up to j. It's a polynomial like that. We take the normal form against the Gröbner basis because we want to write this as a unique linear combination of b. We get something like that. Okay? Then we add, lambda. That just adds, a constant. That was just like the -1 here. That's one more parameter. Right? So in addition to a, b, c up to j, we also have lambda. Everything is linear. Okay? It's an I. Well, it's an I if and only if these are 0. Right? We have a linear combination of standard monomials. Remember, b is a basis mod I. So a linear combination of standard monomials is an I if and only if the coefficients are 0. That's what a basis does. So in a vector space with the basis, you are 0 if your coefficients are 0 in the basis. Right? So that's a linear system of equations. And then you take that, you type it into CVX, Sedumi, solve it, and there you go. Okay? So you get the best lower bound. That's how you solve this real root optimization problem if the ambient complex variety is finite. And I just realized, Spencer, that I lied, because after the 2-minute break that begins now, I will talk about the general case. Take a 2-minute break.